So have a nice day, everybody. I'm Daniel Barath. Let me start the presentation first. So currently I'm at ETH Zurich, but most of this work was done in Prague and also in Budapest. So I included all the logos into the main, into the first slide. But I'm going to talk about today a robust estimation in computer vision. There won't be too much deep learning in it, so it is a deep learning free session, I would say. Okay, so what is the problem basically? So the problem is that we want to find some geometric models. So we aim to finding geometric models. There are, I would say, specialized problems and general problems in this while we do this. For example, I would say the easiest one and the simplest one is the finding of a single model of a single class, basically, without outliers. So that is the easiest problem when we have 2D points, or we have any kinds of points, and we want to find, for example, a 2D line, and that's the problem here. One step harder problem, I would say, is when we have points from the line and also points from outside the line or outside the inconsistent with the model manifold which we are looking for. And in that case, we will need some robust model estimator to solve that problem. And this is what we are going to discuss today. But there are more general problems in this field as well. So we can talk about multi-instance single-class model fitting when we aim to find multiple instances of the same model. For example, we aim to finding multiple lines or multiple fundamental matrices or whatever. Or we can also go for the, I would say that is the most general problem when we have multiple instances of not necessarily the same class. So for example, circles and lines or different classes. During this talk, I usually will use lines as example, but these are general algorithms which can be used to whatever geometric model you have. It doesn't matter. It can, and whatever data. So it can be LiDAR, point cloud, point correspondences, point trajectories. It doesn't really matter. And you can have any kinds of geometric model, but lines usually are the easiest way to understand things and to visualize things. A few examples for these problems. For example, we can have some images of coins, and we can go for estimating circles and lines together. We can have image pairs and go for estimating epipolar geometry. Or so basically, epipolar geometry is the camera pose. It consists of the camera pose and the intrinsic camera parameter. So that is basically the orientation change and the translation change between two cameras. Or also we can have image pairs. These four are, by the way, is my cursor visible?
Yes.
Good, so I can use it to point to things. So these four images are the first images of image pairs. We can go for estimating homographies, so basically planes into image in stereo images. Or we can have some motions. First, this is a video. So we have point trajectories along the video, and we can go for estimating these rigid motions. Or also we can have some LiDAR scans, and where we want to estimate 3D planes and 3D cylinders. Here, that blue points are from a cylinder. So these are some example problems. So it won't be just about line fitting. It is a general problem, and it can solve many model fitting problems. No, wrong button. Okay. So coming back to the simplest case, when we have noisy points from a 2D line, and we have nothing else. This is, I would say, one of the simplest problems in this field. And it's well known, the solution is well known, and it can easily be solved. We simply have to put the coordinates of the points into a big matrix, big coefficient matrix, and then apply an SVD decomposition, and that will give us the least squares optimal solution. So basically, this line will have the smallest sum of squared point model residuals, which we can get. The problem is, and the reason why we need robust model fitting, is the case when we have points not from the line, points which are inconsistent with the model which we are looking for. These we will call outliers from now on, and the points which are on the line will be the inliers. And in this case, least squares fitting will fail. Here another example with another density of points. Again, it fails here. And the main problem is that, okay, that we have a number of points, 100 points from outside the line, of course it fails. But even if we have one very bad point, for example, a point up there on the top left corner of the image, it will kill the least squares fitting. It won't work. So this is the motivation why we need robust model fitting, because if we have inconsistent points which are inconsistent with the model which we want to fit, these square fitting fail. And whenever we go for estimating something from real world data, we always have noisy points and we always have outliers. So this is a problem which cannot be avoided when using when using real world data for estimating some geometric models. Some older solutions, some solutions how to solve this problem. So for example, what is the problem? We are given some measure, some guess of the noise scale. That is what we usually call an inlier-outlier threshold, but that is a noise that should be proportional to the noise scale. And also we have a set of data points, and the task is to find theta prime, the best model which we can find, which minimizes some loss function basically. And this loss function should reflect the fact that that we have bad points as well. So this should be robust. If we talk about RANSAC, which I will show you in the next slide how it works, so maybe it's better to show it now, then the loss function will be more understandable. So basically how RANSAC works, that was proposed 40 years ago, and it still works quite well, by the way. So RANSAC is an iteration. In the first step of the iteration, of every iteration, we select a minimal sample. A minimal sample is a set of points which are enough for estimating the model which we want to estimate. So for example, for a 2D line, 2 points are enough for estimating it. For a 3D plane, 3 points are needed. For fundamental matrix, 7 points will be needed. So the minimum number of points which are enough to estimate it. So we select here, in this case, 2 points at random. We fit the model to those 2 points. And then we measure the distances of all points to that particular model, to the newly fitted model. And then we basically count how many points falls closer than a threshold to this model. So for example, here it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 inliers. So even 11 points which are closer than the threshold. And we consider this number, this inlier count, as a quality for the model. So this was the first iteration. We found a model with 11 inliers. This is so far the best which we have seen. So we keep it, we store this, the model parameters and also the inliers. Then we continue the iteration. We selected this one, and I think it has 10, maybe 10 inliers. So it's not better. It doesn't have more points closer than the threshold than the previous best model. So we do nothing, we just continue. Then we get this, I don't know, this has 15 points closer than the threshold. So this is our new best models. We update so far the best model, and then we continue, and we have some probabilistic guarantees of finding the so far the best model. So basically, this is how RANSAC works. If I go back to the previous slide here, this is what is written here basically. So the loss of a point given a model will be 0 if the point to model residual. So basically the distance of the point from the model is smaller than a threshold. Otherwise it's some constant. So this is this top hat like distance function, which you can see here in the middle of the plot. So this means that if this is some kind of distance signed distance. If the distance is smaller than -1 or 1, that is currently the threshold on this plot. Then there is no loss. I mean 0 loss. Otherwise, there is some constant. So this is what RANSAC does, and of course it's an extremely simple algorithm, and it works quite well. And the question is, should I stop the talk here? And of course, it would be weird if I start this talk after 10 minutes, so I might continue. Because there are lots of things which can be improved to really make RANSAC state of the art. I mean, if you implement RANSAC on its own, it will work quite well, but it's still quite far away from being state of the art. Also, the implementation is hard, and there are lots of components which could be and which were improved since its publication. We can have different cost functions. instead of counting the inliers, we can have some probabilities of how good that model is, or different kinds of loss functions. Also, the setting of the inlier-outlier threshold can be done differently. It's not necessarily have to be set manually, but there are ways to avoid this setting. Also, we can have some degeneracy testing, some chirality checking. I never know how it is pronounced, but I usually pronounce it chirality. This means that we have some visibility constraints on the observed model. For example, if we observe a plane from a camera, then if we find if the plane flips between the two images, that's not correct. I mean, we should see the same side if we found the plane on both images. Also, we can have some local optimization to improve the accuracy of the model fitting. We can have a number of procedures to speed up the robust estimation. So there are many things to improve RANSAC and to really make it state of the art. I wrote into Google Scholar this morning just RANSAC in the search field, and I got more than 62,000 hits from papers containing in the title or in the abstract RANSAC. And also, if I go for papers which has RANSAC in the title, it's more than 1,300. So since its publication, there are several things proposed to improve its accuracy or some aspect of the robustness of its procedure. Today, I'm going to talk about I would say two things. Maybe I will talk about the third thing as well, depending on our time. But I would like to show you ways of avoiding to set this inlier-outlier threshold, and also I would like to show you ways of how to use special properties of the data which we can get of the geometric data. For example, using the spatial coherence, which usually happens when we have some real-world data. So, for example, if I get points from the table in front of me, then close points likely belong to the same table. This is what spatial coherence means in this case. If I want to describe traditional algorithms for robust model fitting, robust estimation, they consider, I would say, the problems of finding the set of inliers and finding the model as an equivalent problem. Since in the standard setting, we always go for estimating the model we always go for returning the model parameters and also its inliers, and it's considered the same problem. So if we have the inliers, the model can be easily estimated by least squares fitting. If we have the model, we can easily get the inliers if we have the inlier-outlier threshold. So there is a crisp inlier-outlier decision which is made. So we, in the end, for sure know what points are in and what points are out. So there is a decision in the procedure. I will show you one method for this later. There is a second approach where we do not really care about finding the inliers. We want to find the sought model parameters. So we want to find the model without doing a strict inlier-outlier decision. And therefore, we don't need, in such cases, a single inlier-outlier threshold. And that is important. I will show you, I don't know, in this slide, in a few slides, so many examples when the setting of the inlier-outlier threshold is not entirely clear, especially if you have some big data set with many images and etc. Then the setting of the threshold is unclear in most of the cases. Some examples for that. So in the standard setting, what we have as input a set of data points, and we have an inlier-outlier threshold. This is what you see here. Of course, this is a synthetic scene, so we have 2D points, and we have 2D points from a line as well. And these blue dotted lines show the actual inlier-outlier threshold. I mean, it should be proportional to the noise scale. So this is basically the noise scale in this case. And what we give, what we return as output, we return the model parameters, the 2D lines, and the set of inliers. This is the standard setting. But the problem in this particular case is that, of course, these scenes were designed to have different noise scales. But if you look at the noise scales, then all of the scenes will require different thresholds to really find the line which we are looking for. If we go for real-world data, this is each plot is a data set. I think the left two plots are for homography fitting. The right two plots are for fundamental matrix fitting. Each bar is a scene from that particular data set. And this vertical axis, basically the thing which we did, we selected carefully and manually inliers from the images. Then we fitted the model to do the inliers, and then we measured what is the inconsistency of that model to the inliers, given the inliers which we use for the fitting. So basically, that is supposed to simulate the case when we know exactly what the noise scale is. So we know exactly what should be the inlier-outlier threshold. And the thing which you can see here is that for all images, for all scenes, this best threshold is quite different. I mean, for this first scene, it's 0.7. This third one is 0.1. And even amongst the data sets, these scales vary. I mean, the scale of the vertical axis vary even for different data sets. So the message here is there is not a single inlier-outlier threshold which suits all scenes, which will be good for all scenes. And therefore, to get the best results, we should tune image by image the threshold, which is of course not doable always. And there are other problems as well with setting the threshold. So for example, we can have some noise in the measured data, some compression artifacts, some noise from resizing the images, and etc. And also we can have imperfect models. So it can happen that we fit some model and it's imperfect because there are other things happening in the scene in the meantime as well. So for example, if there's rolling shutter, so you can see I make the names of the participants smaller so I can see them on the right side of the slide as well. Okay, I'm back. So on the right, you can see this is the image of a helicopter, and on the bottom, you can see the effect, the rolling shutter effect. So this is because most of the cameras capture their scenes, capture the images row by row. So if there is a fast-moving thing in the image, then that moves slightly in between the capturing of two rows. So this is why we see these interesting artifacts in the images. And if we don't consider this when fitting the model, then of course threshold would not even make sense or should be adapted accordingly. Also, there could be radial distortion in the scene, which we do not consider when fitting the model. So these lines are not straight because of the radial distortion. Also, the scene can be non-rigid, slightly non-rigid. So we go for fundamental matrix estimation, which is basically the rigid motion between two images. And if something is non-rigid, the model will be imperfect, and setting the threshold will be tricky. There can be other things again. So we can have imperfect residual function. For example, when we do epipolar geometry estimation, fundamental or essential matrix, we often measure the symmetric epipolar distance, which means that we have a point correspondence, x0 and x1 in two images. And we measure how consistent that point correspondence is with the epipolar geometry, what we estimate, by measuring the distance of the points from the corresponding epipolar lines. This distance, of course, can be measured, but if I get that point and move it along the line, I will never be able to penalize that movement, because I only know that I can only use the point to line distance. I have no other information from the epipolar geometry. Also, there can be other things. So the image, different image sizes would imply that on different. So if I have an image pair, or the left image, if it's smaller, maybe I should use a smaller threshold. If it's bigger, maybe I should use a bigger threshold, image by image. And also there can be problems when we have far and close objects. For example, if I go for finding that a bottle there, this few pixel threshold, this, all right, I would say this is a few millimeters distance. If I want to find a woman in the background, that few pixels threshold, it's now getting bigger. And if I have the moon in the back or the Eiffel Tower or whatever, a few pixels can mean kilometers. So even this thing affects the good threshold in that part for that particular scene and problem which we have at hand. To solve this problem, to reduce the dependency on the threshold, there were a few algorithms, not that much, by the way. So I think this is the oldest one. This was proposed more than 20 years ago. And this is the MINPRAN algorithm, which basically, I will show you, I have a visualization that probably is easier here. So the thing what MINPRAN does is that it gets a minimal sample, like RANSAC. So these two red points here, I stop this now. So, and then fit the line to these points, fit the model to the minimal sample. And then it tries finding the best threshold where given some assumptions, given some probability. So basically it tries to find the best threshold where the inliers, which are closer than a threshold, are the least likely to have occurred randomly. So this is the probability which it uses. But the main idea is to find a model and then try to find adaptively the best threshold which interprets the data the most, basically. And this is what happens here. So for example, if I start at the beginning, it starts by a closed threshold, then it starts increasing it. Every time it recalculates the probability of being a bad model, basically. So this is how I would say, being a bad threshold, it increases. It wants to minimize, wrong button. It wants to minimize this probability, so it stores every time I find a new smaller probability, and then after a while it finds it, and then it doesn't change the stored threshold. So this green dashed line is the so far the best threshold with for this particular line, and this blue one is the currently tested one. So this is basically what MINPRAN does. This is an algorithm which adaptively tries to find the best threshold for that particular problem and line and model. This a contrario RANSAC was, I think, proposed 5 years ago, something like that. So it's a much newer method, and it builds on the same assumptions basically as the MINPRAN idea, as the MINPRAN paper. I would say the major difference between the two papers are the minimized probability. So basically, MINPRAN algorithm minimized the probability of the points being uniformly random, while this algorithm, this a contrario RANSAC, minimizes the number of expected false alarms. This means that it has some assumption about the noise model, and it minimizes the number of points closer than the threshold, which are inconsistent with that noise model, basically. But actually, how it works, how it proceeds, it's very, very similar. So it tries from some small threshold, it tries many of them. Every time it calculates now this number of false alarms, and it stores the so far the best every time. Interestingly, I don't know which algorithm is better. So I've never seen a real comparison of a contrario RANSAC and MINPRAN, not even the a contrario RANSAC paper, but maybe it's better. Maybe most probably it's better than the MINPRAN algorithm. And these were the algorithms which tried. So this is the only two algorithms which I know of which tries to find the threshold adaptively for each model and for each problem. The second method which I want to, the third method which I want to show you will be, was a motivation for us to propose the next method, which I will show you, and that was published at CVPR 2 years ago and last year again, different version. But so this was a motivation for that. This is the random sample aggregated consensus, the RANSAC algorithm. I'm not even sure if it has been published in the end. I think it is on archive still. Maybe it has been published, I don't know. And the idea, the observations motivating this algorithm is, again, setting the threshold is hard. And the second observation is that when we use RANSAC, what happens? We have some reasonably good model with 50 inliers, then we find a new one with 51 inliers, and then we choose that 51 inliers model and immediately forget about the previous best. And the thing which it wants to solve is to do not ignore the potentially useful samples by always going for the best hypothesis. And the idea of this algorithm is that we should combine, so these were the observations, these were the motivation for RANSAC. And the idea is to combine the generated hypothesis instead of using just a single one. And this combination is done by weighted averaging of the model parameters. But there are questions and issues which should be solved to make this algorithm work. First of all, what is an average model? How can we average two homographies? Or how can we average two fundamental matrices? For some models, it's clear, I would say. For translation averaging, it's I would say, a quite easy problem. Rotation averaging is already solved for global SFM algorithms. But if we go further and we want to average affine transformations, projective transformations, I think it's not that clear how to average these transformations, how to average these models. The thing what they propose is to convert the models to points, and then do the averaging on the points over the points, and then convert the averaged point coordinates back to the model parameters, basically. So for example, if we have a homography that can be represented by 4 points. So if we get the corners here, we transform them by the homography, we get these points here, and these coordinates will basically represent the homography which we had before. Also, we can have more complex models, some radial distortion homography like this, which again can represent the homography what we had. And then if we go for, so this is some example, you can see 2 images, left and right, and some point correspondences. Some of them are good, some of them are bad. So for example, the head of that angel is found correctly, while this frame part is assigned to some bird up there. So we have inlier correspondences and outlier correspondences as well. And what happens? We generate many homographies by drawing minimal samples and estimating the model parameters from minimal samples. We convert all of them to point coordinates, so we get these kind of things. I zoom in. So these are one corner, other corner, other corner, other corner. And then we can do some things to get the averaged model parameters. For example, this is zoom in again. For example, we can have, by the way, this white dot there is are the ground truth parameters which we are looking for, but we can have some weighted averaging, weighted mean, weighted mean, weighted geometric median, and whatever. We can use even the RANSAC score, RANSAC type of thing by selecting the best. And this is how the final model is calculated in this RANSAC algorithm. But there are, I would say, a number of limitations with this. It's not clear how to convert a model to a unique set of points. For a homography, maybe I can convert a homography to point correspondences, to points. But a fundamental matrix, I don't know how to convert a fundamental matrix to points. Also, it requires to be able to convert the points back to a model, which usually is clear. I mean, if we estimate homography from points, then we know how to estimate homography from points. But for example, if we have line segments, then we do not necessarily know how to estimate that actual model which we aim to fit from points. Also, there are other theoretical issues, like we have to find a good sample more than 1 times in contrast to RANSAC, and also the weighting is unclear. Other problem with this conversion is it's non-robust. I mean, if we have this scene, this Star Wars scene, we want, and we have the homography representing it. If you convert the homography to points, what will we get? We will get this corner, we will get this corner, and the 2 corners will be at infinity and they will overlap. And I won't be able to differentiate between them. So I will end up with 3 point correspondences, and from them I cannot calculate back the homography. Also, if we have such examples where the plane of the homography flips, so this point gets to here, this point gets to here, moves to here, then again we are not able to convert the homography back in a meaningful way. So this method has a number of limitations. To be honest, I have never seen it really working in practice. But the reason why I still said that, because this motivated the next algorithm. And the motivation comes from the idea of averaging models, of averaging things to avoid using an inlier-outlier threshold. And this MAGSAC, this marginalizing sample consensus algorithm, was proposed 2 years ago at CVPR. And the idea is as follows. First of all, we don't want to make a strict inlier-outlier decision. We don't want to know what is in and what is out. We just need to get the model parameters. And as soon as we have the model parameters, we can have some procedure of getting the inliers. But during the robust model fitting procedure, we don't want to know that. And therefore, if we don't want to know that, we don't need to have a single threshold. So this was the idea. So then there are some design choices how to interpret the data. So for example, we assume that the outliers are uniformly distributed in the scene. That is a quite usual assumption. Also, we assumed that the squared inlier residuals have chi-square distribution. This happens basically when the residual is calculated as the sum of squared variables, where the variables have normal distribution. So if we have squared variables of Gaussian distribution, then the sum of them will have chi-square distribution. And these are just some design choices. Of course, MAGSAC is capable of assuming different kinds of noise model. It doesn't really matter. And by the way, this noise model should be used in RANSAC as well, not just the usual Gaussian or uniform distribution. If we put these choices together, don't worry, I won't go. The equation itself, it's not that important. There are a few things which are important in that. So if I put the assumptions together which we made, just nothing more, we just put the assumptions together, then we can formalize the likelihood of model theta given some noise level. So we know how likely this theta is, this model is, if we have some noise level, basically. And it comes from the outlier distribution, the uniform outlier distribution. This is this part, and that right part is the chi-square distribution from the inliers. So this is how we calculate basically the likelihood of a model given some noise scale. But since now we are able to formalize, to decide to measure the likelihood of model given some noise, we can basically say that we want to marginalize. We want to average out the model parameters. Average out the likelihood. So basically, we get the likelihood of the model. We use logarithm just for numerical issues. It doesn't matter, but we can get the likelihood of the model given the noise scales averaged out over a range of noise scales. So basically, this is what we do. We estimate, of course, if it's easier to understand if you imagine like estimating the likelihood for many noise scales and then averaging the likelihood, and that is the new quality function which we proposed for the model validation. So now instead of counting the inliers, or instead of having some different MSAC-like quality function, we have a new quality function for RANSAC, which does not need an inlier-outlier threshold. It just needs an loose upper bound for that. I will show you later that this loose upper bound can be chosen from a much wider range. So the advantages of this is that it does not make any inlier-outlier decision. And this is an advantage, but it implies a few problems which should be solved. First of all, we have no knowledge about the inliers. And the thing is about RANSAC, so that it always ends with the least squares fitting on all inliers. So RANSAC basically, if we stay at the line fitting, select 2 points, in the end, it will return the model estimated from two points, which has the most inliers. but that still is estimated from 2 points. So the last step of RANSAC always is to get all the inliers and estimate the model parameters from all the inliers by some least squares fitting or something like that, or some numerical optimization, even web markup or whatever. So the problem is that since we don't know the inliers, we cannot do this least squares fitting, and we should do, because that's quite fundamental for finding a really accurate model. And that's another thing, that because of not knowing the inliers, of course, we don't know the number of inliers, and that is used in RANSAC to decide when should the iteration stop. So the determination criterion of RANSAC depends on the inlier number. So these things should be solved. To solve the first one, to solve this least squares fitting problem, we propose this sigma consensus model fitting. And the idea is to get the inlier probabilities of all points, given the noise model assumptions which we have, and which we had, calculate the inlier probabilities for all points, and then apply a weighted least squares fitting using these inlier probabilities as weights. So this is what you can see here. So we have an initial model that is, for example, the output of RANSAC, or somehow we get this model. We want to improve it by fitting to all inliers, and then we estimate the probability of point X given that model. And this is again the same marginalization as what I've shown you before. There is nothing new in it. It's just reformulated to say something about the point and not the model theta. And again, it doesn't need sigma, so this likelihood doesn't require sigma, so the noise scale, to estimate the likelihood of the point. So we have some probabilities for each point, for all points, and then we apply a weighted least squares fitting, and this is what happens basically. I think I have some visualization. Yeah, we get there soon. The next question is how to know when how to stop the algorithm if we don't know anything about the inlier number. So we should need a new termination criterion for estimating the model, for stopping the iteration. And if we have a look on the RANSAC criterion, it looks like this. This means that if we have a model theta and we know the noise scale, so we have some inlier alpha threshold, we have a set of data points, we can calculate how many iterations to do using this equation, where this is a manually set confidence. So basically we can say that we want to be 99% sure that that we found the best model which we could find. This is the sample size, and this is the inlier ratio. And this is what we don't know without noise scale, without a threshold. If we go for the MAGSAC idea, we can simply say, we can do again what we did previously. So we can marginalize over the noise scale. So get this equation and average out the noise scale. So basically it will become the average of several possible iteration numbers averaged out over a range of noise scales. But to make it more understandable what happens, this is an example. Of course, it's not all calculations that are done like this, and it's not sequential, but it helps in understanding what really happens when estimating the model quality. So we have some input model. In this particular case, that input model is from that to points, but it can be anything. So it can be the output of RANSAC or whatever. Then we iterate over the range of noise scales, iterate over the range of thresholds. And for each threshold, the set of inliers are selected, and then we refit the model parameters to the inliers. And these temporal model parameters help in finding the quality function, help in finding the quality of this particular model. So this is how you can imagine MAGSAC working. Some pros and cons, why it's good and why it's not. So in all our tests, it was very accurate, and it had a smaller failure ratio than the competitors. But the problem is that the set and the setting, it's not a problem, it's a good thing. So the setting of this sigma max, so the upper bound of the noise scale, is much easier than the setting of the threshold, which is usually used in RANSAC and other kinds of robust estimators. The bad thing is that this quality calculation requires a number of least square splitting, which can be quite slow in many cases. So MAGSAC is not always slower, of course, because it finds the good model usually early, and therefore it terminates early. That can be slow if it doesn't find the good model early or the inlier ratio is small. And this is what motivated us to propose this MAGSAC++ algorithm. This was published at last CVPR. And the idea is, I would say, the same. So we want to find the model parameters without a single threshold, without doing inlier-outlier decisions. And now we don't assume anything about the outliers. So we don't assume that they are uniformly distributed in the scene. And now this is solved by an efficient iterative derivative least squares approach. The same thing are assumed about the inliers, so they are assumed to have chi-square distributions. It wouldn't make sense to go deeply into the equations, but I just want to show you how it works. So basically, it's an iterative derivative least squares approach. So in each iteration, the next model parameters are calculated from the previous model parameters using some robust weighting function, basically. This weighting function, this weight function is the one which is marginalized over the noise scale. So this is where the marginalization is. So this is why we don't need the threshold again when doing this. And of course, we need a new model quality function, but it's not that important at the moment. The important thing, I think, is that now this quality function can be calculated precisely, because in MAGSAC we calculated it approximately. But now it's precisely calculated, and also if it's very efficient, since most of these calculations, most of these quality calculations can be done a priori and can be stored in a big lookup table, and we just have to do a few operations when calculating the quality or the weight of a point. So to conclude this section. There are methods. Nowadays, there are a few methods which start working without an inlier-outlier decision, and also without requiring an inlier-outlier threshold, because that's an important problem, especially if we have a large-scale data set. Usually, we cannot set the threshold image by image. It should be set automatically, or it should be avoided to even be set. Good. So the next thing which I want to talk about we'll have more colorful images than the previous one. It will be about spatial coherence, but I think this is the right moment to ask if you have any questions of if something was unclear or something like that. So do you have any questions?
I will mention in the meantime any of the slides for this talk, if you could send in the end so we could post them. So people will have access. I need to look at the slides a bit more, to look at the equations to understand a bit better.
Yeah, of course. Yeah. Of course, I will send them. Yeah, I don't see sense in going deeply in depth in the equations now, because it's more about understanding, I think. But yeah, so I will send the presentation and it will be available. Good. So if there are no other questions, let me continue with the next topic. So the thing which I want to show you is how to use a minute. There is this control panel on the top, and I don't see much. Okay, I will imagine the top of my slides. Good. So the problem and the thing which I want to discuss here is how to exploit the tendency of the data, of real-world data, to be spatially coherent. And this is a quite clear thing to imagine. I mean, if we see an object, the table in front of us, the laptop in front of us, or whatever, and we get points from it, then the points which are close to each other likely belong to the same model. So points from the table are close to each other, so they probably are from the same model. Even if we don't know if that is a table, we see only the points, but if they are close to each other, usually they are from the same model. And this is the assumption which can be used in many ways in robust fitting. But there are examples here for this property as well. So this is a two-view motion fitting. This is an image pair. In the two images, this toy is moved. So this car moved to here. That, I don't know what that is, but that moved to here. This bread or croissant, or I don't know how to pronounce croissant, moved to here.
That's how you pronounce it perfect, actually. I should be studying. Yeah.
Thank
croissant.
You.
I like the accent.
So I'm happy then. Good. So this is an example for that, where we have multiple motions, and you can see that the points which are close to each other likely belong to the same model. Here again, this is homography fitting. So the first images of image pairs, you can see again the same thing. For example, the green points, if 2 points are close to each other, they are from the same plane. Of course, it's not necessarily true, especially when around the edges of the planes or the models which we are looking for. For example, here at the edge on the bottom, you can see that there are red points which are assigned to that plane there, but they should have been assigned probably to the green plane there, or who knows. So there are points which should belong to more models. But in general, it is true that if 2 points are close, then they often belong to the same model. This is the same for lighter point clouds. So if we have a plane or cylinder or whatever, or when we have vanishing point, we want to do vanishing point detection from 9 segments. So this is the assumption which we want to build in to RANSAC. I will show you 2 algorithms, one for improving the accuracy in via some local optimization, and I will show you a sampling technique which speeds up the robust estimation procedure by considering local structures. This GraphCut RANSAC, we published it 3 years ago, almost 3 years ago now at CVPR. This is a new locally optimized RANSAC. I will soon tell you what a locally optimized RANSAC is, but I will tell you the idea first. So the idea is that you can see now image pairs. So this is the first image, this small one is the second image. And if I select a minimal sample at random, these green points, and I fit a fundamental matrix, so rigid motion to these points, and then I select the inliers of that point of that model by standard thresholding, I get these points in these inliers in this particular case. If I use the information that points close to each other should be from the same model, we can get more inliers than before. Of course, this is just a teaser image, just an idea what we want to achieve when including the spatial coherence into the fitting procedure. It's a big algorithm. The thing which you can see here, it's basically how locally optimized RANSAC looks. What happens? This part, this repeat anti part, is the RANSAC part, basically. This is the robust estimation. Everything else is the input and the initialization. The first step, as in RANSAC, is the sampling. We get a minimal sample, for example, 2 points at random. Then we estimate the model parameters, for example, the line from the 2 points. And then we do the model verification. So basically, we calculate the quality of the model or count the inliers of the model, whatever we currently use. And then the difference between RANSAC and the locally optimized RANSAC is that in this part, in RANSAC, we simply stored the best model parameters and the inliers. But here, we say that if we find a new best model, we not just store the best model parameters, but we try to improve it. For example, we can get the inliers and do least square splitting or some inner RANSAC or whatever. But the idea is that whenever we find a new best model, we try improving it to find to improve the parameters and try terminating early by finding by improving it significantly. So this is the idea of locally optimized RANSACs, and there can be many local optimization procedures. In this GraphCut RANSAC algorithm, we propose the new one, basically. And the idea is the motivation is to include this spatial coherence of the data into the local optimization procedure. to do so, we have to slightly reformalize RANSAC. If we want to formalize RANSAC as a binary labeling problem, no, that sentence. So we want to formalize RANSAC as a binary labeling problem because that's easy to, for that, it is easy to add additional energy terms, additional losses to be minimized. So it's beneficial for us if we can formalize RANSAC as a binary labeling problem. But the question is what binary labeling problem is. So we are given a set of points as before. We have the inlier-outlier threshold. Of course, we can use MAGSAC here, and we don't need to have this inlier-outlier threshold. And we have the model parameters here. And we want to reformalize the inlier selection of RANSAC as a binary labeling. And the objective here is that we want to find labeling L. And this labeling basically assigns each point to the inlier-outlier class. So basically, it has two labels in this particular case, inlier or outlier, and it is a function which assigns to label one of these labels to all points in the scene. We want that a point to be labeled inlier if it's a residual from the model, so the point to model distance is smaller than the threshold, and we want it to be labeled outlier if it's farther than the threshold. And if we want to write these things down, this is what we get. This is the problem now. So we want to find L prime. So the best possible labeling, which minimizes this energy function. I'm not sure if all of you are familiar with energy functions. Basically, you can imagine that as a loss function, as a penalty function. So smaller is better. So energy is some loss, basically. And the energy, the unary energy, so the unary loss, and unary means that it depends on each point independently. We look like this. Where the the energy from point P is this. This means that we have zero energy, we have zero loss implied. If the point is labeled inlier, here in this case, and it is closer than the threshold. We have zero loss again if the point is labeled outlier and it is farther than the threshold. So basically, they said that it's good if the point is inlier and it's close, and it is good if the point is outlier and it's far. Otherwise, all the other cases are bad. That is not what we want. So there's some constant loss function, constant energy implied. The good thing about binary labeling problems is that they can be solved in polynomial time by the graph-cut algorithm, which is good. And it's, I mean, in globally optimally, they can be solved in globally optimally. And also one thing which is important, that we said basically nothing new. This is what in the previous slide is again simply RANSAC, nothing new, just slightly reformulated, said with different words basically. But the thing why it is good now, because we can include new energy terms into this formulation. So we can construct, we can exploit the spatial coherence or other kinds of energy terms which we see suitable. And that's what we aimed at, basically. The next question is, okay, it's nice that we now are able to use other kind of energy terms, but how to formalize this assumption that close points belong to the same model? And we can have, for example, the POTS model, which says that if we have a preliminary built neighborhood graph, so we get all points, and even before starting robust estimation, we build some neighborhood graph. And this energy from the POTS model iterates through the edges of the neighborhood graphs. And it says that there is some energy, there is some loss if the labels of the points are different. Otherwise, the energy is zero. So this basically means that if 2 points are neighbors, so if 2 points are close to each other, then they should have the same label. Otherwise, they should not. So this is how we reformalize the assumption that close points should belong to the same model, as close points should get the same label in the labeling procedure. If they do not get the same label, then there is some energy which we want to minimize. The problem with the spots model is that it considers that the inlier and outlier class are similar. Maybe it's easier to show it through this example. So this lambda here is the weight of the spatial coherence term, basically. If it's 0, then we don't use spatial coherence at all. If it's 1, then we use just the spatial coherence, and there is no unary term, no residual, point model residual is considered. Of course, it's 0, there's no change. This line selects everything which is closer than the threshold. But the problem is that if this is increased, this outlier structure, so this outlier structure have lots of points. And because of having lots of points, it will start forcing all the other points in that structure, even if they should be inliers, for example here, to be labeled outlier. So basically the problem with the spots model is that there is no difference between inliers and outliers. If it is in a structure, it will try to force everything in the structure to have the same label. And that is not good in these particular cases, for example, when we have an initially not too good model. But the thing which we want is to spread the inlier label along the spatial structure, and by that trying to improve the initial model, even if it was bad. And apparently a POTS model is not the way to go. We therefore propose the new spatial coherence model, which basically proceeds as follows. So if the neighboring points have different labels, we don't like it, we will have some energy, we will have some penalty implied. If the points are assigned to the inlier class, that we like inliers, we like points assigned to the model, so there is no energy. And we penalize only the case where the points are jointly labeled outlier, and we penalize it in a way that it's dependent on the distance from the model. So basically, we say that if the points are close to the model and the algorithm wants to label them jointly to be outliers, then that's no good. No, not good. We want to keep the points close to the line to be inliers, and then spread the inlier label from outside that area that of the selected by the threshold. So this f basically is some robust distance function from the for the point in the model. How it works in this case? So we this new model, of course, we have the same label, same lambda. It's the same weight as before. If lambda is 0, again, there is no difference because there is no spatial model, spatial coherence term. It's turned off. But as soon as we start increasing it, we can see that this acts as we want, basically. So if we increase it, it starts spreading the inlier label along the spatial structure, and that's good. So for example, if we have some inner RANSAC or whatever, when we refit the model parameters to this to the selected inliers, even from this very, very bad model, which is exactly orthogonal to what we are looking for, we can find the good model parameters by just using the spatial structures in the data. This is how it works. I just tell it briefly. So basically, this is the new local optimization. It is an iteration, and in the beginning of all iterations, we do this graph cutting and get the set of inliers given the current model. Then we do an inner RANSAC on the inliers, and then we keep the best model if we have found the new best one. If we haven't found the new best one, then we terminate. And this is how this local optimization proceeds, basically. So this was a way of how to use the spatial coherence in local optimization of RANSAC, how to improve the accuracy. The next algorithm which I want to show you is about how to speed up the robust estimation using this spatial coherence. This NAPSAC algorithm was proposed many, many years ago, and it basically proceeds as follows. It selects its first point at random. So that red point is selected at random. Then all the other points is selected at random, and all the other points from the sample are selected from the circle, from the hypersphere around, centered on this initially selected point. So basically, if we go for 2D line fitting, then the remaining one point is selected from the circle. If we need more points, then again, these are selected from the circle. And why is this good? The reason why it's good is because if the first selected point is an inlier, then the inlier ratio in the circle, in the hypersphere centered at that particular point, tends to be much higher than the inlier ratio in the scene. So for example, in this particular scene, the inlier ratio is 0.84 for this circle, and in the scene is 0.5. So it's much more likely to find a good sample in this case. So this is the NAPSAC idea, but there are a few problems with NAPSAC. The biggest problem is, I would say, is that if I select the first point at random, for example, this one is the first point, and then for this example, I selected all the other points in the circle and fitted a line to them. And you can see that even if I used just inliers, so all of them inliers, none of the lines seem to be good enough. I mean, this is reasonably close, but I would expect more from an all inlier sample. So the problem is that in such local regions, the points tend to be ill-conditioned. I mean, the noise, even a few pixels noise, have a very big effect on the line fitting when doing in such a local area, when using such a local sample. This is one and the biggest problem. But there are, of course, other problems with this NAPSAC, and that other problem is that selecting the good radius for the hypersphere is not clear in most of the cases. I mean, if it is too small, then so if it is too small, then that could be cases when we never find the good model because the distances are bigger. If it is too big, then there's no speed up because we select everything from the. So we select almost all points even in one hypersphere. So NAPSAC is not. I haven't seen it really working in practice, but it motivated the idea of progressive NAPSAC, which was proposed at last year's CVPR. And the idea is to try mixing this local sampling by the global sampling of RANSAC. And the algorithm works as follows. So we similarly as in NAPSAC, select the first point at random. Sorry, I missed the first step. So we assign a hypersphere to all of an independent hypersphere to each of the points. And then during the sampling, we select the first point at random, like in NAPSAC. And then we try selecting the sample from the hypersphere centered on that point. If for some iterations we do not find that sample, we do not find a good model, we start increasing the radius of the circle. So we start blending back to the global sampling, which we had in RANSAC, for example. And of course, after a while, if we don't find anything, then it will degrade back to the uniform sampling of RANSAC. Why it's good? Because it tries to combine the benefits of both approaches. I mean, for small circle, for localized samples, the inlier ratio is high, so we have more chance of finding a good sample, but it's poorly conditioned, so usually, even if we found a good sample, it's not good enough, but maybe it is, so maybe we can use that information if that is the case. For big circle, it's good because it's conditioned, so if we find a good sample and with points reasonably far from each other, that usually will end up with a good model. But a bad thing about it is that the inlier ratio is much lower than before. We have some growth function. So we had a function how to increase the size of the radius. I do not think it's very important to say now, but it's based on statistics, and yeah. So
yeah, we don't have to dive into it now.
Yeah, that's what I think as well.
Yeah.
Good. So these were the some ways of these were some ways of using the spatial coherence for improving the accuracy and processing time and speeding up the robust estimation procedure by finding good samples early. And if you have any questions, I'm glad to answer. If not, I will go forward, and I have some experiments to show to you which works how and such things. How well. Do you have any questions? Let me check what's the time. Good, we have time.
Yeah, we do. No questions on the chat, so I think we can continue for now.
Good. So for this CVPR tutorial, we made lots of tests and lots of evaluations for different problems, which algorithm works, how well. And also we evaluated some deep learning approaches and tried to see what is the position, how should these deep learning approaches used together with different robust fitting algorithms and etc. So this is the goal here. The first thing which I want to show you is for fundamental matrix and accession matrix estimation. So we have image pairs, and we want to find the relative pose between the images, basically. So the orientation and translation change between two images. We used the Phototourism benchmark, Phototourism Dataset, which consists of 26 scenes for SFM. So they contain thousands, 10,000s of images, around 30,000 of images, which are enough for estimating, for checking the quality and the accuracy of such robust estimation algorithms, I think. Some other statistics about the data sets. Basically, this is just to see how big these are. So each scene from the data sets usually have around 1,000 or at most a few thousand or at least a few hundred images, and with at least 500,000 3D points in the end after the reconstruction. So we used the ground truth from core map reconstruction to get some ground truth on which the algorithms can be evaluated. We tested lots of robust algorithms from the Scikit image, OpenCV's RANSAC, OpenCV's least median squares, and many other kinds of algorithms, since we wanted to see not just the algorithms but the implementations as well, how they work. Because to our experience and experiments, there are two things which make a robust estimator work. First thing is to have the state-of-the-art components. That is the first thing. But the second thing is almost as important as the first thing, is that we want to, it should be implemented really well. And there will be an example for that soon. And also, besides these traditional algorithms, we asked the authors of some deep learning-based papers to provide us results, and these are also included in this evaluation. And I think what you can see here, each bar is a method, and the vertical axis basically is the mean average accuracy. So this is the accuracy. Being higher is better in this particular case. And the most accurate result, this is for fundamental matrix fitting for 1K iterations, with a maximum of 1K iterations inside RANSAC. And the best possible results were obtained by combining this GC RANSAC, so this spatial coherence thing, with DeGenSAC, which I haven't shown to you. That is a different algorithm proposed by Ondrahum a few years back. And this MAGSAC++ scoring without the inlier-outlier decision. There is another plot. This is not from, this is from this paper published at IJCV last year, comparing different methods. And the thing which you can see here is the horizontal axis is a threshold to considering results successful, basically. So we estimate fundamental matrix, then we decompose it to pose, and then the pose error is measured, and that is some degrees. So for example, the rotation has 2 degrees error, the translation has 4 degrees errors. So on average, the error is 3 degrees. And this says that if we consider everything successful, which has smaller than 5 degrees error, then that increase the push up the curve, otherwise it will lower the curve. So this basically is the success rate given some condition of what success is. By the way, this is what is shown here. So these values are the areas under these curves. And the thing which you can see here, again, the same as it was visible here. So the combination of these proposed algorithms goes the highest. So this is the most accurate method for fundamental matrix fitting on this particular data set. I wanted to show you one thing, and it's not here yet, so I will show you later when I get there. I want to show you USAC. It's here. So this is, again, for the fundamental matrix estimation, 1K iterations. And the thing which you can see here is USAC is a universal sample consensus algorithm, which was the combination of many algorithms which were state of the art at that time, and that time was, I don't know, 6 years ago, something like that. So not like 20 years ago. And this USAC contains DAGANSAC as well. And interestingly, this DAGANSAC is more accurate than USAC in this scene. And the reason is the different implementation. So the available USAC implementation is, I would say, not that good. And even if it contains the state-of-the-art components at that time, it is worse than a well-implemented DAGANSAC, which simply does the degeneracy testing besides doing the fundamental matrix estimation. So I think it's an important message. Having a good implementation is as important as having all the state-of-the-art components. One other thing, which is an interesting thing for here. So if you remember, I have told what AC RANSAC is earlier. This is the a contrario RANSAC, which adaptively selects the inlier threshold. And it can be seen here that if we don't set an upper bound for the threshold, it doesn't work. So it still needs some upper bound for setting the threshold. If we set the threshold, set an upper bound, it works reasonably well. It's not the best, but it works reasonably well. Then the interesting question was how good are those deep learning methods, which are proposed year by year on the most prestigious conferences like CVPR, ECCV, ICCV for computer vision. And actually, on their own, they are not that good if we really estimate, if we apply them on this quite big scene and quite big data set. If we get the learned methods and get their inliers, which they return, and then apply DLT, so least squares fitting, they are not too good. Even if without learning, state-of-the-art methods like MAGSAC++ is much better than all of them. But I think what we saw is that they are actually smart ways of pre-filtering the points. So basically, the thing which leads to the most accurate results on these data sets and in our problems is to get the inliers, which these deep learning based approaches return, and then apply some state-of-the-art RANSAC on the top of those inliers, on the top of these methods. And this is how we got the most accurate results in the end, basically. And that is, I think, an interesting message. I mean, it's interesting to see that they are not really for fundamental matrix estimation or homography estimation in most of the cases, but they are smart ways of pre-filtering points for some robust estimation in the end. Of course, we did some tests for essential matrix estimation as well with almost the same algorithms from OpenCV and whatever. And also for the deep learning approaches. The same things can be seen here as for fundamental matrix estimation, nothing surprising. So I don't think it's important to stay at every slide. So it's again the same. So the combination of the deep learning based approaches and these modern RANSACs led to the most accurate results in the end. If we go for homography estimation, so that in this case we want to we have two images, an image pair, and we want to find a plane-to-plane correspondence, and we want to and it's inliers as well. And we used the Hpatches-Sequences datasets and the extreme view dataset to evaluate the methods, and we split them into validation and test sets, so we can set the hyperparameters of all methods, and also we sent them to the authors of the deep learning based papers so they can train their algorithms on them. We again compared lots of methods implemented in Python, implemented in OpenCV, and whatever. Interestingly, here on these particular problems, GC RANSAC without anything was the most accurate one for homography fitting. But the same things can be seen here. So USAC is supposed to be amongst the best according to the components which it contains. Still, it's amongst the worst performing ones. AC RANSAC here is okay, it's in the middle. It doesn't need any, but it needs an upper bound for the threshold. Without the upper bound, it ends up like here. And yes, this is the same things can be seen here for the methods as previously. But I think now the most interesting thing is, these are just new plots, it's not that important. The most interesting thing is how sensitive or how insensitive these methods are to the setting of the inlier-outlier threshold. So I have told you a number of methods which don't need a single threshold, and they just need an upper bound for that, which can be chosen from a much wider range. But the question is if it's true. And we ran, I don't know which button did I, okay, I came back. So we ran an experiment. I think I forgot to write the problem, but this is fundamental matrix estimation, essential matrix estimation, and homography estimation on the right. The horizontal axis shows the inlier-outlier threshold or its upper bound used for the method, while the vertical axis is the accuracy of that particular method. These plots are slightly misleading, I would say, because these horizontal axes are shown in a logarithmic scale. So the left part of this figure is much, much smaller in reality than the right part of this figure. And you can see that in the right part MAGSAC++ is on the top. So this means that it is the most stable algorithm over a wide range of inlier-outlier threshold. So it is more insensitive to the setting of the threshold than the other methods. To make this clearer, we can calculate the areas under the curves. So we can calculate the areas under the curves, and that could be a measure of how insensitive or how sensitive a method to the threshold. This is now the insensitivity, so higher values are better. And the same thing, we saw the same thing as in the plots. So basically, methods which do not need, which just need the upper bound for the threshold are much less sensitive. So for example, MAGSAC++ is almost always the least sensitive, or MAGSAC is the least sensitive to the setting of the threshold. And also AC RANSAC, which if I go back here, which was in the middle in terms of maximum best accuracy, is quite good when checking how insensitive it is to the setting of the threshold. Of course, its maximum accuracy, if we set the best possible threshold, is not as high as for the other methods, but it is reasonably good if we have no idea about what should be the threshold which we use. And the take-home message from this, I think, is that robust model fitting is not trivial, and setting the threshold is not trivial in most of the cases, and it requires, I think, a lot, and it still has lots of challenges to solve. I mean, okay that we have some upper bound for the threshold now, but how to solve the problem without really setting a threshold, and there are lots of things which are unsolved. But these real-world data often provides us some insights about what can be used for the fitting, for example, the spatial coherence, or something for the threshold setting, or whatever. And this was and thank you for your attention. I forgot to write. I think I don't have time for the multimodal fitting part, so this was the end. Let me turn off my alarm clock, so I have to wake up a minute.
It's a nice alarm clock with birds singing.
And I'm back. I'm ready if you have any questions. I have seen the chat window a few times.
Oh yeah, well, there was 2 questions on the chat. I was waiting for us to finish to go over them. First, Michaela is asking, of course, she says, thank you for the talk. She's asking, but what about the execution times of the methods?
So I don't have such figure. I don't know why I don't have such figure, but usually we talk about, in most of the cases, these are real time. I mean, most of the algorithms which you can see here are real time. Of course, that depends on the particle problem. So if we have 100,000s of point pairs, points, then nothing will be real time basically. If we remove many of the points, but in most of the cases, all of these are real time. We are talking about tens of milliseconds in most of the cases in usual problems. Did I answer? Michaela.
Hi, I'm Michaela.
Hey.
Yeah, so it was just like to understand if it's clear for you what is the best trade-off between those methods if we consider both execution time and accuracy of the method.
Yeah, so as I said, usually they are a few tens of milliseconds at most. So MAGSAC tends to be slightly slower. Yeah, they are comparable. MAGSAC tends to be slightly slower sometimes, but again, the slightly slower means that, I don't know, 10 milliseconds slower or something like that. So they are comparable in terms of processing time. One thing which I forgot to say, and I'm not sure if they were in the slides, but all of these methods which I've just shown you have available implementation on GitHub with Python binding and with Jupyter Notebook example and with whatever you want. All of them are implemented, by the way, in C++. So you can even try and see how fast and how good they are.
Okay, thank you very much.
I don't see the link. I will add the link to the PowerPoint and then
yeah,
the link, if you could,
the link will add on to the link to the lecture slide, so we'll have it. That's not the same ones, right, that we posted on the event?
Yeah, they are the same ones, so it's quite easy then. So they are posted for the event, but I will put them into the PowerPoint as well. But these are GitHub links basically, so you can go there and check everything.
Yeah, GraphCut RANSAC and MAGSAC.
Yeah, that one that contains everything.
Perfect. Michaela, any more questions?
No, thank you very much.
Thank you for the question.
Ina was mentioning number of iterations in RANSAC should be also estimated. This is currently out of the scope of this presentation. It's a question.
What? Okay, number of iterations in RANSAC should also be estimated. No, it was said. So RANSAC usually have a clear termination criterion depending on the confidence. I think I even had that in the slides. So that depends on the inlier ratio and the confidence. And for that, we proposed a new one for MAGSAC++ for MAGSAC to avoid having the inlier ratio. But yeah, so it's also included. So it's an important thing when to stop with iteration. It's here actually.
I think she was maybe referring.
Different one.
Yeah, it's also from Ina. In Zuliani paper, there is estimation to number of iterations. Maybe she's with regard to processing time, maybe to estimate how many iterations are expected usually with the algorithm until convergence.
I haven't read that Zuliani paper, or maybe I don't know which paper are you talking about. You mean the number of iterations? Yes. Okay. So reporting the number of iterations. But the question, is it important? I mean, if I run 2,000 iterations and each iteration takes half millisecond, or I run just 2 iterations and each of them takes 2 seconds, then it doesn't. I think iteration number is not really important. The important thing is how fast we are in terms of walk log time, so in terms of processing time, and how accurate we are. Iteration number, of course, are related to the processing time, but not necessarily. Did I answer?
I have a question regarding that. You mentioned before polynomial time computation, right? So that polynomial, that's actually
that's for the GraphCut. That's for the GraphCut, and it's applied very rarely.
Okay.
she or he, I don't know. Maybe you can ask in the microphone so we can discuss why you don't agree.
Okay, I'll try. Because, for example, you are looking for line, and you're like it's very crowded, even if you have two lines. So it may be that if you don't make enough iterations, you even don't sample the points that represent this line. So you should be sure that you did enough iterations to hit at least 2 points that or 2 points that belong to this line. And I think that this is what is at least what I read this paper a long time ago, but at least he tries just to estimate the number of iterations that is required as well.
Okay, but what if you have a so good sampler that finds the model in the first iteration? That is the ideal sampler. That is why people use different kinds of samplers, not just the uniform sampling. They use PROSAC, NAPSAC, progressive NAPSAC, and there is this NG-RANSAC nowadays, narrowly guided RANSAC, which are different samplers. And the idea of them is to find the model from as few iterations as possible. So maybe one iteration is enough. It depends on the sampler you use and the scene.
Okay, I can think about it.
Good.
It depends, I think. On the concrete example, probably.
Yeah, so this is why I said that a number of iterations, it doesn't really say much. The thing which say much is how long it took to find the model and how good is that. That's what I think. Maybe I'm not right, but that's my.
And just a question, in fundamental matrix estimation, you need pairs of matched points. In fact, your point is like a pair of points that were already matched into images. And does it depend on the matcher itself? Because your like algorithm with matches point may be also not so good. So
yeah, of course. So the first, I think the first step to really make accurate, really estimate an accurate fundamental matrix is to get good point correspondences. If you don't have good correspondences, then the robust estimation won't solve that problem. So that is. I think robust estimation is the second step in this. First, you need good correspondences. Then a good robust estimation can provide you an even better model, a very good model. So as you said, it's very important to find good correspondences, and there are lots of methods for doing it.
But in your case, like outliers is bad matches.
Yes, exactly. But look, if the matcher provides us, I don't know, 10 good matches and 1,000 bad matches, nothing will solve that situation.
Okay. Thank you.
Thank you.
There was another question by Uri. Here just wrote another message also. I think the question is, how is the combination of deep neural networks and those methods usually work, or it works generally?
I don't necessarily understand the question. I mean, you can combine them in a way how we did. So like we got results from the deep neural network and then we did our algorithms on top, or maybe we can combine them probably directly. There are a few methods for them. To be honest, I'm not really familiar with deep learning, so I might be not the best person to answer how to use deep learning inside RANSAC. There are a few methods, for example, this NG-RANSAC, which basically learns, as I remember, which points usually are good and which points usually are from the model manifold. And it is a new sampler to try to sample points which are more likely to be good in the end from the learned knowledge. But again, other combinations, there might be lots of combinations, unsolved combinations and unpublished combinations, which could work very well. It's I would say, combining robust estimators and deep learning is a quite new problem. And I've seen papers about it just in recent years.
So...
Oh, let's go from the top. On the top, there are lots of questions. I mean, not lots of, but a few from Ina.
Yeah, we covered them already.
Okay, good.
We did. No worries. Let me just check on YouTube if there are any there. No, I think there aren't. We have 9 people still watching on YouTube here.
Oh,
Can I ask just one question?
of course.
So I liked one of your formulation is find and to estimate rigid motion, and I don't remember. So with special correlation, you just assume that object is like it's like specially local, and you find inliers. So inliers are also like belong spatially correlated, if I understood correctly the idea. So does it give you this method? Does it estimate the motion parameters well, or you can simultaneously solve both problems, like segmentation problem and motion estimation simultaneously? Because it can be really interesting problem, because in a way, if you know that this is an object, you will make estimation of motion parameters only using these object points. But so can you just reformulate this problem? But it's just solves two problems simultaneously. This is my question. Like,
I understood the question, I think. And the current, so we are talking about GraphCAD RANSAC, I think, and where we did this binary thing, and then we selected the inliers. Am I right? So
you had even better
yeah, with this video.
Like,
am I right?
And points. I don't remember, but
okay. But the question is if I get the inliers and the model parameters simultaneously, and the answer is I do not. So first I get the inliers, and then I estimate the models using some discursive or inner RANSAC. I don't know of any methods which do this simultaneously with this considering the spatial coherence. If you want, we can write it and publish a paper about it.
But it can be interesting.
Yeah, it can be. I agree.
Okay, any more questions, people? Anybody?
But there was a question with this attention mechanism. I have no idea about attention mechanism.
Yeah, that's about deep learning. Yeah.
Yeah, but I remember that 2 years ago there was some paper where they claimed that the network makes RANSAC. There was some paper like this.
There are a lot of papers. All deep learning papers says that they are better than RANSAC. This is how they start usually. And this is what we wanted to check when doing this tutorial for this RANSAC in 2020 CVPR tutorial. This is what we wanted to check. And as I said, the thing which we saw that they are not better or worse than RANSAC. They are complementary things. So together with RANSAC, they are quite good and they improve. Without RANSAC and without robust fitting, they do not improve. So just applying a DLT here, you can see just applying a DLT to the output of the learn methods, it's quite bad. If we combine them and we consider them as complementary things, then they improve. And yet, you're right, all of the deep learning papers doing robust fitting of fundamental matrix estimation says that they are better on RANSAC. It's I think, more, there are more details to it.
But I think that probably for deep learning, it's better just to use functions that are more robust, like Hooper function. There is also papers of John Baron that uses like metrics that are robust to big errors or something like this one, because probably it shouldn't be RANSAC. But,
yeah, but then the problem is so you need some robust thing, and that is not easy to model deep learning. Again, I don't know about deep learning much, but yeah, so some I think in CONSEC, and what was that? CONSEC is multiple fitting. In DSEC and DSEC++, Eric Brachman formulated slightly different. So without this maximus, he used some softmax instead of the max in RANSAC, which worked quite well. But that is for relocalization, so not for solving a new unseen problem in a robust way, but relocalization to a scene which we have seen already.
And another question, with your example of having radial distortion, fisheye cameras, It seems that if you don't solve this problem, it's just no point to use RANSAC at all, because it just doesn't follow the model itself.
Look, there are models. You can fit radial distortion homography. You can fit radial distortion mathematics. That was just an example to say that there are cases when we do not consider such models, such such problems. There are cases. So there are cases when there's a very small radial distortion, and we don't care about it. We just go for homography estimation, and that was just the motivation part, I would say.
And do you think that there are papers that related half transform together with RANSAC? Because if you think about it, there is some kind of similarity.
Yeah, there are lots of papers with half transform doing similar problems, but I don't know if nowadays lots of people use a half transform.
No, I'm not speaking about half transform, but if anyone just some paper that tells the similarity between them and uses like back and forth methods or tricks from one method to another one, because there is similarity. For example, one of the ideas, probably it is done. You can take RANSAC, don't work with like inliers-outliers, but measuring like quality of your sampling, and then just having many models like this one, and use models that are close in parameters and close by quality, and combining them, something like this one. And this resembles half transform in a way. So,
yeah, I haven't seen such paper. That doesn't mean that there isn't any, but I haven't seen.
Okay, I think this is a good time to finish.
Thank you for the attention.
Daniel, thank you for the talk. Very focused and informative. Even though it's a tough topic, at least for me, this is not usually my subject, I was able to follow. So really, I thank you again for giving us this talk. You can see also the comments now in the chat. Everybody's saying great talk.
Yeah. I will make a print screen then.
I'll send you the chat if you want. I'll send you the recording of the chat. Thank you. Sure. I already sent links to everywhere where you can find the community. This talk is now on YouTube Live. It'll be recorded on YouTube as well and posted. Along with the lecture slides, we will post them on Reddit soon. Thanks everybody for tuning in, and I will say bye and until the next time.
Thank you. Bye.
Bye-bye.